each other. So there's a magnetostatic interaction. And this magnetostatic interaction affects the anisotropy energy that I was talking about. We need a system, a particle with the high anisotropy, so that the interaction with the neighboring particle does not affect the state of magnetization of the particle. So there's a magnetostatic interaction. So we need to also understand this magnetostatic interaction, how much this interaction is, and how it's going to influence the overall behavior of the system. So we need to identify and quantify these interactions. See, when we talk about a magnetic material, uh, particularly the ferromagnetic material or a ferrimagnetic material, the magnetization of such a material has normally two contributions. One is the irreversible contribution, and other is the reversible contribution. So when you start magnetizing a system, first the magnetization and the magnetic field vary linearly. So normally this happens in the initial stages. So after the magnetic field is sufficient enough, if you try to reverse the magnetic field, the state of the magnetization does not return to its initial state. We call that irreversibility has come into play. Reversible processes are those where if you get back your magnetic field to the initial value, your magnetization also gets to the initial value. But this irreversibility is there, and it because the in a ferromagnetic system or a ferromagnetic system, the state of magnetization depends upon the history. What was the initial state of magnetization? It decides what will be the next stage of magnetization. So there are both contributions to the magnetization, reversible as well as irreversible. As you can see on the right of this slide, the reversible component does not show hysteresis. It means if a system obeys in a reversible manner, then you can vary the magnetic field so the magnetization changes, and then if you bring back the magnetic field to initial values, the magnetization also turns into the initial values. So these reversible components are there, but irreversibility, as I said, is important because it is this irreversibility that gives the porosity to the system, and we require this porosity. We want that the system should retain the information. So we need to quantify these reversible and irreversible processes in a system. Now, why I'm telling you like this, when we normally look at a typical hysteresis curve, when we see a hysteresis curve, this is a typical hysteresis curve. You start with a zero magnetic field and you start increasing the magnetic field until the system domains start aligning in the direction of the magnetic field. Initially, from zero magnetic field to up to certain magnetic field, the system is reversible because from this state, if you go back to, you will have the same magnetizations every point. But as you start increasing the magnetic field, the magnetic domain regions, they start aligning, and finally at saturation all the domains are aligned in one particular fashion. So when you reverse the magnetic field, as you know, you don't, when you reverse the magnetic field, you do not trace the initial path of magnetization, but the path is traced where you have a remnant magnetization. So all this creates a hysteresis, and that hysteresis is basically what decides how the material, what will be its porosity. So as I said, irreversibility is here a blessing. Although in many situations in physics, we don't need irreversible processes. We want that everything should be reversible. Now, some parameters are important to understand this reversibility and irreversibility. Like right at the porosity, at the where the porosity, we normally find the derivative of magnetization with respect to the this magnetic field. We call this the switching field distribution. This is called the switching field distribution. As you can see, a Lorentzian type of a curve over here. It tells you how much your switching field distribution is in your system, how your particles are behaving. Actually, we require that this distribution should be as minimum as possible. We require that this distribution curve, which is here as a Lorentz, shown as a Lorentzian, should be like a delta function, like a Dirac delta function, so that the porosity happens at a particular magnetic field. But of course, there's a distribution. we need to look at this distribution. Now, see, when we characterize magnetic materials, normal method of characterizing a magnetic material is to take the hysteresis law, what we call as the magnetization as a function of magnetic field. By doing that, we only get an information about the magnetic material, which is an average information. It's a statistically averaged information about the magnetic particles in the system. We never know about the interactions within the system that are happening, and we never know what are the reversible and the irreversible components in the system. So there's a method, as I said at the very outset, developed in the University of Oxford by Professor Harrison. This method, known as the first order reversal curve method, it's a method that is used to understand the interactions and the porosity distribution. This first order reversal curve method, it can provide an insight into the relative proportions of reversible and the irreversible components in the system. It also helps us to characterize a system via distribution of local porosities. And in addition, we can also understand the local interaction fields. I will come to that. This slide gives you a brief about what this fourth method can do. Now, this is not something a rocket science, this method. Only in order to do this experiment, or in order to understand this, you only need a vibrating sample magnetometer. And that vibrating sample magnetometer can be programmed to do this fourth or first order reversal curves, and then understand the microscopic behavior of a magnetic system. So let me first come to the formalism. What is fourth formalism? As you can see in this slide, on the left side, you'll see an hysteresis. We call this as a major hysteresis loop. And on the right side, you see many number of loops that are inside the major loop. So we call them as forks. They are known as first order reversal curves. Now, when we talk about a magnetic system, and we model a magnetic system by saying that a magnetic system is made up of small particles. Those are basically, they can be basically like nanodots, or they can be some particles which have aggregated together to form a magnetic system. For such a particle, fork formalism requires that they should behave like what's known as the hysterons. So you see the hysteresis curve of a hysteron. It's an ideal hysteresis curve. We call this as a Prasek model, which considers a material to be a collection of square loop hysterons. And our each particle, our each nanodot has a hysteresis which looks like this, at this square loop. It has two states which are characterized by up and down switching. So we call this down switching A and up switching B. That means at a magnetic field of A, it switches down, and at a magnetic field of B, it switches up. This hysteron, this hysteresis curve is an idealized, and each particle now is known as a hysteron. As you can see, it is symmetric. From the y-axis, that's the magnetization axis, the distance up to the switching field is called the porosity. So you can see the porosity is constant. But if there are other particles present in the system, these particles can interact with these hysterons. So there can be interaction among the hysterons, and that will shift our our hysteron, and it will generate what's known as a local interaction field, this HU. So the hysteron will shift, and either it can shift onto the right of the symmetry curve, or it can shift onto the left of the symmetry curve. So we call one as a positive shift and the other as the negative shift. This shift tells us that there is an interaction field. The interaction field is present. So this is the basic model, which is known as a hysteron, which we call as our smallest particle, the nanodot, which behaves as a histron. Then once we understand that our system is made up of these small histrons, we have a collection of those histrons, and those histrons may have all the same, they can have the same porosity. Therefore, all of them will switch at a one field, or they can have distribution of porosities. To understand that, what we do, we describe what's known as Price-Sachs distribution. This is a function, a distribution function of A and B. See, what is the A? These are the switching fields. A, when the system switches down from upstate to downstate, and B, when it switches back from downstate to the upstate. So if we collect information about all the histrons, and then plot them on a graph, which is a graph where one coordinate, one axis is HV, another is HA. HA is the switching down field, HV is the switching up field. And this line running diagonally, it's known as the Price-Sachs plane. Then these small dots, as you can see, these small red colored dots, they represent the position of a hysteron in this Price-Sachs plane. This dotted curve is known as the porosity line. The position of a dot on the porosity line tells us what is the porosity of the hysteron. See, this one, the second Price-Sachs plane, here the dot is far away from the origin. It means it represents a hysteron which has more porosity. Below are given the hysteresis for the hysteron that is represented at point C, and another hysteron that is represented here. As you can see, the porosity of this hysteron in the middle is large as compared to the porosity of the hysteron which is here. So in this Price-Sachs plane, the position of these hysterons tells us about their porosity. And if there is an interaction among the hysterons, then this point will shift about this porosity line, about this dotted line, it will shift. So if we have a hysteron shifting towards the right of this porosity line, we say it's a positive shift. It means now there are interactions, and if it shifts onto the left side, then we say there are negative shifts. So shifting of this point on the porosity line tells us about the interaction. So this is a model how Price-Sachs way back in 1928 modeled a ferromagnetic or a magnetic system comprising of large number of particles, and each particle behaving as a hysteron. Now see another interpretation of this Price-Sachs interpretation. How Price-Sachs interpreted this magnetic system. Again, we are in the Price-Sachs plane. The red line in this Price-Sachs plane is known as the reversibility line. All the hysterons above this reversibility line are reversible. As you can see here you have these hysterons, their hysteresis, but as you can see, these hysteresis do not show the loop, so we call them as reversible hysterons. Whereas the hysterons that are below this red line, they show us the irreversibility component. So all the hysterons that are represented below this red line into this plane, they are irreversible components of your magnetization. So all the hysterons, they are just which lie on this porosity line tell us that far away they are from the origin, more is the porosity of that hysteron. Here I show you in blue color, there's a diagram which is basically known as the Fock diagram that we'll talk about later. It basically tells you this Price-Sachs distribution. It helps you to plot this Price-Sachs distribution, this distribution function, and it allows you to understand how your system is behaving, how your magnetic system is behaving. So once again, to make you clear, what I am showing here is a Price-Sachs plane. In this Price-Sachs plane, we have a reversibility line. Above this reversibility line, all the hysterons show the reversible contribution to the magnetization, and below this they show the irreversible contribution to the magnetization. Farther the historon from the origin, like this, the larger the porosity of that historon, and obviously the histons onto the right of the this positive curve show a positive shift in the in this, and the negative shifted histons. So once we understand that how a magnetic system comprising of large number of particles behaves, now we go into how we actually do this experiment, and after doing this experiment, how we plot this price-act distribution. So once again, I want to emphasize on this reversible and irreversible magnetization components, as you know. So both components are present in our system, and the irreversible component normally gives rise to the hysteresis, whereas the reversible components, they do not give rise to hysteresis. Okay. So let's see what's the conventional hysteresis method. How we basically do the M versus H, the famous experiments that even we do in our colleges or universities to make understand the students what's the hysteresis, how the ferromagnetic materials behave, why they have hysteresis. So if we start with saturating a sample and then reduce the magnetic field in the opposite direction, and then again go back to the again to the saturation magnetic field, what we get is a curve which we call as a hysteresis loop. This is basically normally known as zero order curve. I will tell you why it's called a zero order curve. But this is the way when we do our hysteresis, when we do our magnetization versus magnetic field experiments. We saturate a sample, then bring the magnetic field back, reverse the magnetic field, once again increase the magnetic field, again go to the saturation point. Whatever the magnetization data we get, we plot that magnetization data as a function of the magnetic field, and the result is a hysteresis curve, as you can see here. We call this as a zero order curve. But what happens if we just change this scenario? What we do is, once we saturate a sample, a material, after saturating it, we start reversing our magnetic field, but we don't go to the complete reversal. We don't go in the opposite direction, complete opposite direction. At one point of reversal, we switch back. So we define a reversal field. So again, once again, see, we saturate a sample, then we reduce the magnetic field, and instead of going to the full negative regime, we reverse our magnetic field at one point. So we call this as the reversal field. So this H is the reversal field. So once we do this, from this reversal field, we once again saturate the sample. We do this continuously. Next time we do it for next reversal field. So we...
Sorry for interrupting.
Yeah.
Sir, may I ask something?
Yeah, please.
Okay. Sir, ये जो reversal field, the value of reversal field can be changed?
Yeah.
Or is it fixed? Or depending on the material? Or we can do from our side?
Yes. Basically, if we have a material, see, some materials are well known. People have done so much of work on the materials, and they have understood all the type of hysteresis for that materials. So only you need to know the major hysteresis loop of a material. So if your major hysteresis loop of a material shows you that your porosity is about 1000, then your reversal field, you can reverse your field from, let us say, from 900 onwards. At every step you change this reversal field. You saturate your sample, then reverse your field, stop at one field, and once again start saturating. This way you will get continuously many loops. These are called the minor loops. We call them as minor loops.
Minor loops, right?
Yeah.
In those loops, we can't get the saturation of them.
No, you can't get. You only need to saturate your sample after every reversal, and again once you saturate, you again go to the next reversal, and then again saturate. Go to the next reversal, again saturate. This way you will get a distribution, a kind of a curves. We call them as first order curves.
Okay,
See,
in one quadrant we get the saturation, right? And in
yeah,
other quadrant, okay, okay,
yes. See,
okay.
there
So
is
in
another method, what we call as a second order curve. So
okay,
instead of saturating your sample, you reverse back at some point and then saturate.
okay,
You reverse back and but that's another method. Here I will talk about this first order curve. So once again, try to understand this way of saturating a sample. We are reducing the magnetic field, but we are not going to again full reversal.
full
At one point, we are reversing back our and once again saturating our sample.
okay,
So let's see what happens when we do this. Let's try to see from this model what is actually happening when we do this. See, when you saturate your sample, see the figure number 1 here. This is again Prysak plane, what I was talking about. When you saturate your sample, you expect all the domains of your system aligning in one particular fashion, as are these red arrows. They all point in one particular fashion. So once you start reversing the field, see the see the figure number 2. So here, as I once again see this green dot, I start reducing the magnetic field, and then I stop at some. As I start reducing the magnetic field, but I don't go to the full reversal. What will happen? Some of the domains or some of the particles of the system, they will reverse their switching. They will reverse their state of magnetization, but others will not do it. Others will only do if you go to the through the complete reversal. Then the others will do. So then what we are doing in the third figure, what you are doing, you are once again increasing the magnetic field. Therefore, the what you will see that the earlier particles, those which have switched in the green color, which have switched their magnetization state, many of them again start switching up. So this way you continuously do it. What you are trying to understand the irreversible behavior of the particles. What is the irreversible behavior of the particles? See, if the particles would have been reversible, if the system would have been reversible, then even if you switch your magnetic field from saturation to this reversal field, all the particles would switch back. They will start switching back. See, in the figure 1, you have all these arrows, red arrows pointing up. In figure 2, you have reduced the magnetic field, but some of the regions have shown the change of state of magnetization, as shown with the green arrow. But if the system would have been reversible, then the other systems should also start showing the reversal of the field. But it doesn't happen. So once you again increase the magnetic field of saturation, what happens? Some of the particles start again switching back to the another state of magnetization, whereas the others retain it. So this retention of the state of magnetization of some particles gives the what is known as the irreversibility. It tells us the hysteresis has come from the word history. It means the system is remembering its history and then it is behaving further. So by changing this reversal field at after every line, we get a data, and what we get basically is this. As you can see here, this is the major hysteresis loop. Within the major hysteresis loop, as you can see these parallel lines, here it is a little bit magnified on the right side. As you can see, these are the parallel lines running parallel to each other. What every point here means that we have saturated our sample. After saturating our sample, we are reducing the magnetic field, and then reducing the magnetic field, then we reach up to certain reversal field, and after that we again increase the magnetic field, saturate it, again decrease the magnetic field, again increase the magnetic field. This way, every time we change our reversal field, we get series of curves. We call them as first order reversal curves. So the idea is that by doing this experiment this way, we'll be exploiting the irreversible and the reversible components in the system. So this is the typical first order reversal curve. इसका envelope जो है, the envelope of this is what's known as the major hysteresis loop. So why it is important? The major hysteresis loop only tells you about the an average behavior of your system. But if you want to know what is happening microscopically, how the particles in the system are reversing their magnetic fields and how they are interacting with each other, then we have to repeat this experiment every time. Typically, we need 100 curves or more than 100 curves to form a Fock diagram. And this experiment on a vibrating sample magnetometer takes sometimes 2 days to 4 days. We put our sample in the vibrating sample magnetometer, program it, give the steps, what is the reversal field, and what are the steps of the external magnetic field, and then leave it. After 3 or 4 days, we come and then we collect our data and then process that data to understand the behavior. So this is a typical Fock. Now, once again, I can come back to the Precise plane. Once again, I remind you, this is the reversible line. This is the reversible line. It tells you that any point above this reversible line gives the nature of a reversible component, and all the points below this give the component of the irreversible. So what we do in an experiment, we saturate a sample. We saturate a sample. We saturate a sample and then reverse the magnetic field. Once we reverse the magnetic field, for example, let's suppose we saturate a sample at 2000 oysters, and then it saturates at 2000 oysters, and then we start reversing the field, and then we come back to say minus 1000 oysters. Let's suppose it's minus 1000 oysters. At this minus 1000 oysters, we stop and start increasing the magnetic field again in the forward direction. So by this way, so this is our first reversal field. Let's suppose it is minus 1000. Then we do steps and increase the external magnetic field and note down the magnetization. Again, we saturate the sample. Now, this time we take another reversal field. Let it be minus 1200 oysters. Again, from this reversal field, we increase the magnetic field in steps. Then third curve, then fourth curve, and fifth curve. So this way, at every point, when you say at every point in this diagram, each point represents a reversal field and the applied field. So there are two coordinates. So our magnetization is now a function of these two coordinates. One is the reversal field, and other is the applied field. Reversal field is kept constant for each line, and only the external magnetic field is varied. Next time another curve is drawn, while the reversal field is changed and the magnetic field is again increased in steps. So this way we get a magnetization data. So that magnetization data is then plotted. Here it's a color plot of this magnetization data. It tells us about the colors tell us about the magnitude of that magnetization data. We normally call it as a magnetization surface or a 2D magnetization surface. Here the values of magnetization are color coded. They are shown in the color code. They are not shown as the numbers. So once we do this, once we collect this data to get the magnetization surface, so what's the magnetization surface? It is the value of magnetization in the Precise plane as a function of the reversal field and the applied magnetic field. So once we get that we normally use colors to represent the values of the magnetizations. So once we get the magnetization surface, now we have to find out the Precise distribution or the Fock distribution. Now we have to look here from this data, the magnetization data, what is our Precise distribution, what's our Fock distribution. For that, we normally do a mixed derivative, a partial derivative of magnetization with respect to the reversal field and the applied field. Now, what will I will show you what will this do. So this is our equation, or you can say this gives us the Precise distribution. The sigma, this gamma, this sigma is the rho is the Precise distribution. It gives you the how your hysterons of your system are behaving and what is their position in the Precise plane. So here, if you see in this diagram, we have a magnetization surface. After we perform this second order partial derivative to our magnetization, first taking the derivative with respect to the reversal field and then taking the derivative with respect to the applied field, we obtain a distribution which is again shown color coded over here. And as you can see, this distribution is now concentrated on this core steel line, on this HC line. All other blue colored means zero, it means nothing. But the colors which appear here, such as red or yellow or green, they are concentrated about that core steel line. They tell us about the information about our system. Now, to do this derivative normally, in order to do this partial differentiation of magnetization, we know the magnetization, what we get is basically a data.